Good evening, everyone that's joined. Welcome to the 13th annual Legacy Lecture. For those that don't know me, my name is Brad Brickman. I'm the Vice President of Medical Student Council here at the University of Toledo College of Medicine and Life Sciences. We're excited to be able to host this event during the pandemic, and thank you all for joining from the comfort of your homes. Today, we're pleased to welcome Dr. Andrew Beavis. Dr. Beavis has been part of the college since 1982, back when it was called the Medical College of Ohio. He started as a research associate and then continued to become a professor within the Department of Physiology and Pharmacology up until his retirement this past year. He has received many honors, including the Dean's Award for Teaching Excellence and the Outstanding Faculty Award several times. He has taught numerous students from many programs within the college, including the Biomedical Sciences program, Nurse Practitioner program, Physician's Assistant program, and the MD program. Dr. Beavis served on editorial boards and peer-reviewed many journal articles during his time, as well as authoring 60 publications. He has served on numerous committees, including the Medical Student Admissions Committee and the IACUC, or the Animal Use Committee, of which he was the chair for 15 years. Besides all these huge, tremendous academic achievements, Dr. Beavis also contributed to the arts on campus. Some of you may be familiar with his photographs in the Mulford Library during the annual Artists Showcase. Today, he'll be sharing with us a little bit about his life as well as his time here at UT. He's been an important member of the community here, and I hope you all enjoy his story. And then with that, I hope you give your full attention to Dr. Beavis as he'll now start his presentation.
Okay, let me hit my share button here and hopefully select the right thing. Click here. Okay. Well, I want to thank Brad Brickman and the other members of the student body for inviting me to give this legacy lecture. And I get very nervous when I was invited to do this because I get no idea what I was going to talk about. And so I came up with this title here. How did I get here? Obviously, I didn't want to give a pharmacology lecture or anything like that, but I could not avoid putting some science in here. In fact, I read in some of the literature about this lecture, people talk about it as like the last lecture. And it's not too encouraging as you get to be an older person. But actually, if this is my last lecture, it is actually what I've done is I've gone right back to the very beginning, and it really is the same or a continuation of the very first lecture I gave at MCO in 1982. And so it might say that we didn't progress very far in all that time. And so it's a kind of explanation of how I got to be where I am, sitting here, retired in Toledo area, in Ohio, in the United States. And so once I was accepted to do this, I don't know why I accept things that are scary, but I think that's the only way you kind of progress in life. And it was kind of quite an experience because it made me almost relive in my brain when I was trying to sleep the last 40 years or so of my life, if not more. So if any students are there who know when I teach things, I like to start at the very beginning. And often this goes back quite a way. So I'm going all the way back to kind of 1964 here, if you like, if not earlier, when I was about 12 years old, right, in 64. And at that time, I had finished elementary school. I lived in England, of course, and I enrolled in or was accepted into what was called the Sheen Grammar School. And the UK grammar school is a school which runs basically what we would call the 6th to 12th grade here. The first 5 grades are in elementary school, and a grammar school was kind of designed for students who, at the age of 12, it was determined that they were possible candidates to go to university. So the teaching style and subjects and other things were kind of more tailored towards that. So I guess in some ways I was somewhat privileged. And back then I had no idea what I wanted to do or what I was good at or anything. But I put a couple of notes on the screen here. You know, when I was very young, like many people who go into medicine, science, and other things, we have this intrinsic kind of desire or interest in finding out how things work. We want to know how it works. And when we're little kids, we take things apart and see what's inside. And when I was in this grammar school, I think I named 2 teachers here, Mr. Chapman and Mr. Black. They were the biology and the chemistry teachers. And I named them because they were kind of inspirational, if you like, in the fact that the way they taught the subject, they taught it in a way where you felt they really wanted you to understand what it was all about and not just memorize a list of facts. And I think that's what kind of caught my interest in those subjects. I put here a little note, summer 1969, teaching was when I basically, in retrospect, discovered that I liked to explain things and how things work. And in the summer of 69, I just finished what had been the 10th grade, and I was at the end of my 16th year. And I met a girl on a bus. And that girl ended up actually being my wife. She was in the 9th grade, a grade below me. And as I progressed through the last 2 years of what we call the 6th form, equivalent to 11th and 12th grades, where I studied only basically biology, chemistry, and physics, she was a year below in another grammar school nearby. And I discovered that we spent a huge amount of time discussing things like the electrochemical series. And I had to explain things to her. And she was not an easy person to explain things, or was a good person to try to explain things to, because she would not accept just everything I said, and made me think. And I kind of basically discovered at that point that teaching something really probably benefits the teacher more than the student. And I ended up doing pretty well and got interested in, as you might guess, biochemistry as a mixture of biology and chemistry. And I put 2 names down here, Steve Luzio and Paul Luzio. I got a picture of Steve Luzio as he looks today. I found it on the web. He was my best friend basically from the 2nd grade on up. And I've been in contact with him over the years. And he too was interested in the sciences and kind of biochemistry. But the connection is the fact that he had a brother, Paul Luzio, who was 7 grades above us. And as we entered this grammar school, he was entering the University of Cambridge to study biochemistry. And he, as I say, to do a degree, and he got a PhD there and became a biochemist. So he was a kind of a figure who we could look to say that this was a possible path to take. And in fact, both of us were very interested in doing that. I actually looked up Paul Luzio too. He's 7 years older than both of us. And he also, both of these guys are still working. I find all these people that I used to know years ago and find they're still working. And here I am, retired. Anyway, they're kind of getting towards the end, but they're still at it. So I focused on biochemistry. I did pretty well in my biology, chemistry, and physics. And I got a place at the University of Bristol, where the biochemistry department was relatively new. It was populated by a whole bunch of faculty who had been recruited from Cambridge University. And Paul Luzio told us that they were very good people and this was a good department. And it wasn't that easy to get into. You had to have good grades. And but I got accepted, and so I did an undergraduate degree in biochemistry, which involved the first 2 years of all the honors chemistry as well. So it was, a tough program. And during that time, I've got a picture here, kind of fuzzy one from the web, of Brian Chappell. And Brian Chappell was the chair of the Department of Biochemistry at Bristol. And I put him there because during that time, he gave a lecture on mitochondria and bioenergetics. He was the chair of the department. He didn't actually teach very much and only gave this one lecture. And probably looking back, he wasn't that good a lecturer. He didn't do a lot of preparation, but he talked about bioenergetics and how mitochondria make ATP. And that's really what caught my imagination and attention. And he told us glycolysis, everybody knows glycolysis. Glycolysis can make ATP, especially when you're anaerobic. And what glycolysis, I got glycolysis here in case anybody forgot it. I think this is the first metabolic pathway anybody ever learns. And basically the principle was you get something like glyceraldehyde 3-phosphate, it gets oxidized and a phosphate binds to it, and then another enzyme transfers that phosphate to ADP to make ATP. A very simple chemical reaction, the two things stoichiometrically related. And so this was what we call substrate level phosphorylation. So when people were looking for how mitochondria made ATP, they knew the respiratory chain, oxidation of NADH. Lenin just showed that many years earlier. And they thought, well, it's going to work like glycolysis. So they searched for phosphorylated intermediates, subunits of the respiratory chain that might bind ATP or ADP, and no one could find any such subunits. So it did not appear to be like glycolysis. And he told us that Peter Mitchell, a British scientist, came up in 1961 to explain this. He invoked what he called the chemiosmotic hypothesis. And this is a very simple, this is why I like simple things. So I think this is why it attracted my attention. I didn't have to write down a lot of notes. It was a very simple idea. And his idea, of course, was the respiratory chain, shown here on the left, oxidized substrates, electrons go to oxygen to make water, and these things pump protons. You generate a proton gradient, an electrical and chemical gradient, and this gradient then, by the protons flowing through the ATPase, mitochondrial ATPase, drives the synthesis of ATP. So the two things were not physically connected at all, except by the electrical potential across the membrane, and the whole thing driven by a proton current. And when I saw this, I thought this was really interesting, exciting, and didn't take a lot of memorization like glycolysis does. And so that was Mitchell's hypothesis. This is a picture of him, actually, I took in 1986, so we jump forward a little bit here. Peter Mitchell, as you can see, he got the Nobel Prize in 1979 for just developing that very simple hypothesis. There wasn't a lot to it, but it stimulated research in hundreds of labs throughout the world and led to probably thousands of publications. And so he got the Nobel Prize in 1979 for that. I took this picture in 1986 in the summer at a conference, small conference, to celebrate the 30th anniversary of the reconstitution of the respiratory chain, actually. And I put this image in my lecture when I talk about this to graduate students. And what I asked them when I showed them the picture is, I said, what do you see going on in this picture? And what I'm expecting them or wanting them to see is on the left is the Nobel laureate, who everybody thinks must be a very smart person. What's he doing? He's listening to a graduate student explaining his ideas and work. And I think this really says something that I don't need to explain. He was a listener. He listened to people. He didn't just sit there spouting out, telling people how things were. He listened to what they have to say and responded appropriately. Okay, so having been inspired by this mechanism, after I finished my bachelor's degree in biochemistry, I spent my whole life, I think, I discovered a few weeks back, months back, that I probably spent my time trying to avoid going out to get a job and work. So when I finished my undergrad degree, it seemed the obvious thing to do to avoid getting a job was to go get a PhD. And because that young lady I mentioned about that I met on a bus was also a student there now, of course, and she hadn't finished her degree because she was 1 year behind, I obviously wanted to stay in Bristol, and I chose Brian Chappell's lab to do a PhD. And what did I work on? Well, obviously I wanted to work on something related to the bioenergetics that I had learned, the chemiosmotic hypothesis, and two questions that people often ask, I've written here, are how many ATPs do mitochondria make when they reduce oxygen? Seems like it should be a simple question. And how many ATPs do you get when you oxidize, metabolize one glucose? For some strange reason, people seem to be obsessed with this. I never really understood why, but I know my daughter, when she was in the 9th grade, this came up in like chapter 3, and she didn't understand it at all. But anyway, how many can we make? Well, you turn to thermodynamics. Thermodynamics always has to be fit any model. And basically, you have to have the energy released from the oxidation of NADH can be used to make ATP. So you always need to expend more energy than you conserve or use to make the ATP. And when you look at the key free energies, you got 52.6 for the oxidation, 16 to make one ATP. So it's pretty clear. Don't need to be a mathematician really to figure out that you can make 3 or less ATPs. That's how much energy you've got. You can't make any more. So when people reconstituted the respiratory chain and found that there were 3 different segments of it which could drive ATP synthesis, it became like, people might say, a no-brainer that the PO ratio was 3. But no one knew how it was made, as we said. However, with Mitchell's hypothesis, the hypothesis was the coupling is between the proton gradients. Proton gradient generated by the respiratory chain used to drive synthesis of ATP. So that adds a couple more thermodynamic limitations, and Mitchell suggested 6 protons were pumped for every NADH oxidized. That means if we multiply the chemical potential for the protons or electrochemical potential by 6, this has got to be less than what you get with this, which basically meant the proton gradient had to be less than 379 millivolts. Not too difficult. But on the other hand, when we look at the synthesis of ATP, it showed that in order to generate an ATP by the proton gradient, and if you only had 2 protons moving to make each ATP, which you needed to have a PO ratio of 3, you needed a gradient of 347 millivolts. That's a big potential difference across a thin membrane. And almost everybody who ever measured it up to that point had values which were 200 or less, which is clearly way too low to be compatible with this hypothesis. So what was I going to do as a graduate student? I was going to solve all these problems, or Brian Chappell thought we ought to anyway. And we were going to measure the membrane potential and figure out why everyone else's values were too low. And we did this by measuring radioactive rubidium uptake into mitochondria catalyzed by this antibiotic valinomycin, simply a cyclic peptide that transports rubidium and potassium. You know, rubidium and potassium are very similar. So, very simply, the I don't know if you can hear my dumb noises, but they've been playing for a long time. So the model is, if these are the proton pumps, generate the proton gradient. Protons can only come out if you dissipate, or the potential won't grow anymore if potassium or another charge, positive charge, goes in the opposite direction. And if these things come to a steady state or equilibrium, then the concentration gradient, potassium in over potassium out, since the potassium is going in the mitochondria, is very simply dependent on the electrical membrane potential. So by measuring the potassium gradient, we could calculate the membrane potential. And so that's what I spent months doing, trying to find conditions which we could get a nice stable measurement that did not decay with time, indicating that the mitochondria were damaged or we weren't at a stable state. And I figured if I double the volume, since mitochondria are osmotically active, if I double their volume, that should double the amount of potassium inside if it is free, the amount of rubidium inside if it's free. And I did that, and the numbers I came out with were the electrochemical potential of the protons was around 200 to 220. And I was pretty convinced of this. And so basically the project failed because I didn't show that it was up above 300 that was needed for Mitchell's hypothesis. So I hadn't really contributed anything new. So we didn't publish anything. I did notice, however, which comes up later, is that if I didn't keep the pH at the right value, and I didn't prevent the inside of the mitochondria becoming alkaline, they did become very leaky and could not maintain the potential. It collapsed quite rapidly. Okay, so meanwhile, in the rest of the world, if you like, Klingenberg showed that the ATP transporter transported 4 minuses for 3 minuses on the ADP. And so with the phosphate transport involved or consumed 1 proton going into the mitochondria. And others looking at the ATPase found that it seemed to pump 3 protons for each ATP or thereabouts. That meant 4 protons were actually needed to make any ATP. And that would really screw up the PO ratio that was recognized and would not fit with Mitchell's numbers. However, at the same time, Albert Leninger, the famous biochemist in Johns Hopkins in Baltimore, and Martin Brand, who'd been a graduate student in Brian Chappell's lab, and several others had shown that the mitochondria could take up more than 1 calcium per energy conserving site. And since calcium's got more than 2 charges, they concluded it must be 2. And therefore, the respiratory chain pumps 4 protons per site. And since it takes 4 protons to make an ATP, your PO ratio is back to where it ought to be at 3 for the oxidation of NADH. So everything had suddenly changed. I put Brand in quotes in bold there because he'd been, like I say, he'd been a graduate student in Brian Chappell's lab, and he'd gone to Baltimore as I became a graduate student, and he came back just as I was graduating, and he's still working, and here's a picture of him. When I was an undergrad, he was a first-year graduate student. He didn't quite look like that, and I remember, I hope he's not listening, he was chasing all the first-year students. But anyway, so he came back. He's still working too. He's out in California at the Buck Institute, I think. Anyway, so a lot of people still at work. Scientists don't like to stop. Okay, so everything was back to normal, if you like. And as I mentioned, Martin Brand came back to England, and Brian Chappell asked him to be on my defense committee or my examination committee. So you have to read my dissertation and ask lots of questions and then say, okay, you pass. So given that contact and those contacts we had with the Leininger lab, it seemed pretty like a good idea, since I wanted to come to the US, to do a postdoc with Leininger. And he was willing to take me and my wife, who was also doing a PhD at that time. So since she was a year behind me again, I had to stay an extra year. And so I did a year's postdoc with John Holbrook. Now I call this the lost year because just about that time we split up. That is, my wife and I split up. And so I had to hang around, basically, which ended up doing pretty much nothing for a whole year. And I did not take that time to publish any papers that I could have published. I did some work on factor 13, or I used factor 13 isolate as a clotting factor from coagulation. It was used to connect fluorescent probes to proteins. But anyway, the year went by. I drank a lot of beer and no papers got published. And at the end of that year, I came to the United States and never really been back. And ended up in Leininger's lab. Here's a couple of pictures of him. Leininger, of course, as I mentioned, he's done many great things in bioenergetics and had shown, basically, apparently he's the person who showed the mitochondria were responsible and had all the machinery for making ATP. And from all his great works, he became chair of the Department of Physiological Chemistry at Johns Hopkins at the ripe old age of 35. And here's a couple of pictures of him. What my new problem, so when I get there, of course, I have to have a project to do as a postdoc. And the first problem was that the delta mu H value, for example, that I measured, not that anybody really cared, seemed to be too high for Leininger's high stoichiometries of 12 protons per oxygen. For example, it's okay 12 protons being pumped, that energy has to be split between all of those, and the membrane potential can only be 189 or less. So now, instead of the problem being the membrane potential isn't high enough, which I tried to prove it was higher when I was a graduate student, now the value I got was too high for the new numbers. And that was a little perturbing, so most people ignored that problem. And so what was the second problem? The second problem was most European labs, they started off, remember, Mitchell originally proposed only 2 protons per site, but they kind of agreed with Leininger 4 protons at site 1, 4 protons at site 2, but they only wanted or saw 2 for the last segment of cytochrome oxidase oxidation. That meant the total was not 12, or they believed, but 10. This, of course, means that the pH ratio now is not 3:2 for NADH and succinate, but only 2.5 and 1.5. Okay, it's lower than everybody had thought. So my project, since I was in Leininger's lab and he was paying me as a postdoc, obviously I needed to prove that he was correct and everyone else was wrong. Probably not a good way to start a project, but so I thought, well, if the pH ratio for succinate is only 1.5, according to the Europeans, and 2, according to Leininger, and cytochrome oxidase would therefore, oxidation of cytochrome C would also be very different between 1 and 1.5. So I thought I'll just measure pH ratios and see what they are, and I'll prove Leininger's right. Very simple. However, the first thing I did was, no one really argued at that time that succinate didn't have a pH ratio of 2. Okay, so I thought I'll measure that, show it's 2, and then go on to the look at cytochrome oxidase. However, I couldn't even show that the pH ratio was 2. Maybe it was too low because the mitochondria are somewhat leaky to protons. So I developed a bunch of procedures, or a procedure, which would measure an upper limit and a lower limit. And obviously, the real value must be somewhere in between those two numbers, the mechanistic stoichiometry. But my big problem was my upper limit values were less than 2, which was not what I wanted to see, or not what Leininger wanted to see. So after a few months, I said, okay, well, let's look at the actual protons that are being pumped, or the actual potassium that the mitochondria could take up. So I went back to the old use of valinomycin to transport potassium, i.e., instead of measuring the equilibrium concentration rate gradient, I used a potassium electrode to measure the uptake of potassium, how fast it went in and how fast they consumed the oxygen, and to see how they were related. And here's a picture of me actually in Leininger's lab at a piece of equipment which we were using to do that kind of work. Over here is an oxygen electrode chamber. There's an oxygen electrode stuck inside. It's a potassium electrode to measure the potassium, so we can measure those two things, add the valinomycin, the mitochondria, and everything else. And back then we didn't have computers, so we had to record everything on a chart recorder. Then I'd sit down with a ruler and a pen and measure all those rates and extents manually. This is actually a fake picture. I show it to the students just to see if they recognize me. But this was in 1979. This was actually the apparatus that Antonio Villalobos used, who was my kind of big buddy the first year I was in Baltimore, and he did his experiments there. He was the kind of guy who liked to come in to work at noon and work till 8 or 9 at night before leaving again. And I had a similar kind of schedule. I came in late, got the mitochondria, which were prepared by noon, did my experiment, did my analysis, and then because I had no car, he would take me, often drive me home, or we'd go out and have a few beers or a dinner or something. And so he was a great companion there for the first year I was in Baltimore before he went back to Spain. In fact, because he suffered polio as a child, and he had braces on his leg and needed crutches to walk, and his health wasn't too great, I wasn't sure whether he was still around anymore. I hadn't heard from him for many years. So I Googled him, and lo and behold, Antonio is also still working. His hair kind of changed color, but he's still doing research as an emeritus faculty in Spain. Okay, so when I did those experiments, I looked for the upper limit of the amount of potassium taken up per oxygen with succinate. And what did I find? The upper limit was less than 8. And I was trying to prove that the upper limit was over 8 so that Leininger would be right. So again, it was inconsistent with what we wanted to show to prove that Leininger was correct. I got my visa extended from 2 years to 3 years, kept working, and then I got it extended for another 6 months, kept working, and then I got extended for another 3 months and kept working. And then I stayed 2 months with no pay to try to complete the work. But the bottom of the line was really after 3.5 years of work, the project had failed to prove Leininger stoichiometries were correct. And you lay in bed at night or in the morning when you wake up and you ponder the universe and how many papers you haven't published in your lifetime, and decide that, what am I going to do? Is that the end? And after a while I thought, well, maybe the data are correct. Maybe it's not 8. And all the data I got seemed to indicate that that may not be the case. So what was the conclusion was then, everybody, here's a respiratory chain, 3 complexes. Complex 1 pumps 4 protons. No one argued about that at all. Complex 3 oxidizes ubiquinone or ubiquinol, pumps 4 protons. No one argued about that at all. Complex 4, cytochrome C oxidase, pumps X protons. And let me just move my little picture over a bit here. And so Leininger's lab, they suggest the number is 4 and the pH ratio is 3. Mitchell and the rest of the world, if you like, suggest that it only pumps 2 protons and therefore the pH ratio is 2.5. And I suggested it was 3 and the pH ratio was therefore 11/4 or 2.75. That seemed to fit everything. The question was, who was going to believe me? It took a lot of courage, I guess, for me to go to Leininger's office and suggest to him that what he'd been running around the world at every big scientific meeting, convincing everybody that it was 4, that he should change his mind and say it's 3 because I thought so. And as you might guess, he, even though he was the nicest kind of person, perfect gentleman, he did not want to do that. So what happened? I had no papers published, and it seemed like I had no job prospects. Okay? How can you get a job if you didn't publish any papers when you were a graduate student, or almost none, and you didn't publish any when you were a postdoc for 4 years? So that's where the Toledo connection comes in, and I met Keith Garland. I titled this Keith Garland to the Rescue. He was a guy I met, I think, at a few meetings, and I remember meeting him someplace and discussing mitochondria, and he was very interested in what I've been doing, and I was very interested in what he'd been doing because he studied the KH antiporter, a transporter in mitochondria which exchanges potassium for protons. He proposed that that was involved in letting potassium out of mitochondria to prevent them swelling due to the big electrochemical gradient for potassium across the membranes. And I realized that some of the things I'd seen, like the uncoupling when mitochondria swell with valinomycin present and other things, that this may be due to his potassium proton antiporter. And just by chance, he had a grant funded at that time and invited me to come to Toledo. And I came here and I gave basically this lecture up to now to the pharmacology department, which he worked in. And I decided to come to Toledo instead of going back to the UK and having no job at all. And I was very lucky that Dr. Ascari, who was the chairman of the department, after I'd been there for about a year or something, he offered me a faculty position. So I was no longer a postdoc. And I've listed several other, or all the other chairs of the department that I've had since I've been there, Dr. Rosenberg, Dr. Abraham, and most recently, Dr. Bina Joe. And all of them have been very helpful to me over the years in various ways. And okay, so twice. Oh, see, I'm giving this lecture before, so there's a few technical glitches in there. This is a picture I took of the lab. That's why I'm not in it. This is Keith Garland, and we have some fellows from China, from Norway, and India, and all around. There was quite a big group he had working there, and I think not all of those were there when I first arrived, but they came. Okay, so what did we do there? We did some studies on the KH antiporter. I studied the effects of pH and magnesium on its regulation. And while we were doing that, I also discovered that something else was activated by the same factors, pH, magnesium, swelling, and things like that. And this other thing was a transporter of ions. appeared to be an ion channel. And we called that the inner membrane anion channel. Basically, we kind of discovered it. Obviously, we weren't the first. Someone else had discovered it and called it the pH-dependent anion-conducting pore. But I discovered that the two things were the same, seen from a different point of view. And I spent a lot of my research time in an independent project studying this so-called channel, and got very nice, outlined or discovered, characterized all the properties of it. Now, I got his name, Aníbal Verchesi, on this slide. He was someone who has been a postdoc or a visiting professor, really, I guess, at Lenin's lab. He would go there, spend 6 months, 9 months, a year. And so I'd met him several times. And he invited, well, he didn't invite himself, I invited him to come and do some work in Toledo. And he came in 1990. And here he is with my daughter, who back then was about 6 years old. And we studied potato mitochondria. We stopped at Kroger's every morning, peeled, chipped, and put the potatoes in a blender, and then isolated them just like we did rat liver mitochondria. In fact, they look just like rat liver mitochondria. And we found, he wanted to look at another channel in there, which we looked at some, but then we did other experiments and showed that these mitochondria also had a inner membrane anion channel, which was very much like the one in rat liver, but was slightly different. So we called it PMAC, for potato or plant inner membrane anion channel. And we published that. And Aníbal, apparently, again, I Googled him the other day, and he too is still working, even though he's several years older than I am. He's got more hair, but it's obviously a lot wider. So another figure in the story. At the same time as I was in Galed's lab at Toledo, I was still working on the 4 papers that I had written on the work I'd done in Baltimore with Leninger. And during that time, he had a couple of other postdocs trying to do new refined experiments to kind of prove that the stoichiometry really was 4. And they published those kind of experiments done as a rebuttal to my studies, if you like, in 1984, because they came out before mine were published. And I put a little note at the bottom here. About that same time, I got married again to a woman who I'd met in Baltimore previous year. And in fact, it's quite funny, really. I always tell a story. Dr. Gardy let me off for the morning as long as he could come to the wedding. So we went down to the Toledo courthouse, got married, and then we came back to the pharmacology department and had a reception in the coffee room. So we have a tight connection to the pharmacology physiology department. Okay, so 1986, accelerating along a little bit. I could say it was a very good year. January 13th, I was still working on revisions to the stoichiometry papers with Leninger. The first 2 had to be published before the 3rd and 4th could be published. And these have been sent in September of 85. And they wanted revisions, so we were revising it. In February 3rd, we had a very big site visit for Dr. Ascari's program project grant, a multi-million-dollar research grant involving multiple faculty members. And that very same day, we had a birthday. What was that birthday? That was the birth of my second daughter, which we call Catherine. My wife went into labor the night before, February 3rd. I spent the whole night in Toledo Hospital, and Catherine was born. I went home about 6 a.m., got dressed, and went into the site visit, meet with the team, give my presentation. And the mitochondrial person on that committee was Catherine Lanoux. So I slipped into my presentation that I was I was a little dozy looking is because I've been up all night. My daughter was born, and we were going to name her Catherine right after Catherine Lanou. Of course, I was lying, but we got funded, so that was a good outcome. Okay, February 13th, March the 4th. As I said, I was working with Leininger revising this manuscript, and they were wanting more revisions. And when I called his lab to speak to his secretary, she said, I better make the changes because he was not well. And he died on March the 4th at the age of 69 in Hopkins Hospital. Very unexpected for him to die at such a young age. And the older I get, the younger 69 is looking. March 13th, those papers were accepted. And I was very happy. I've been waiting a long time. In June, we all went to Baltimore for a symposium in the memory of Al Leininger. It was meant to be to celebrate his life's works, but he died in the interim, so it became a memorial symposium. And then in August, I went to another symposium, which was one where I showed the picture of Dr. Leininger. And in the meantime, I've been working on the second two papers, and in August, the second two of the Leininger Lab stoichiometry papers on the potassium ratios got accepted. And in November, another paper was accepted in which Garland and I had summarized all the data and some experiments proposing the existence of that inner membrane ion channel. So we could say 1986 was a very productive year. The question is, what happened with the stoichiometry story? When Leininger died, he was obviously the one arguing for 4 protons for cytochrome oxidase. Everyone else wanted 2. So what happens when one half of an argument dies off? The argument ends. And who wins? Those who are advocating 2 protons per oxygen. So that got kind of accepted and put into textbooks. And this meant that the PO ratio would have to be 2.5. Now, I was absolutely sure the PO ratio from my measurements was more than 2.5. So I never really believed that and was waiting for someone to come along and do some structural studies with cytochrome oxidase and prove it pumped 3 protons. But I waited, well, we were waiting a long, long time. The answer to the problem came in 2010, and it was related to the one assumption that everybody made and no one questioned, and that was that the ATPase in the mitochondria pumped 3 protons per ATP. ATPase, as you all probably know, is an enzyme. It has these alpha beta subunits, 3 of them, which bind the ADP, make ATP. It has a stalk, and these C subunits that bind the protons carry them basically through the membrane, and that whole thing rotates. This gamma subunit in the middle rotates, causes a conformational change, and this is what drives the ATP synthesis. And this is a very neat model, and this was a lot based on the work by Paul Boyer and also John Walker. And here's a picture of Paul Boyer at Leininger's Memorial Symposium, and he got the Nobel Prize in 1997 for his work on the structure of the ATPase. Al Milvan was another Hopkins faculty who was working in X-ray crystallography. I got no idea who this guy was. Why did he get the Nobel Prize in 1997? I don't know, but my guess is that some Japanese guys, Hiroyuki Noji et al., did a very simple experiment. They stuck an ATPase on a glass tab, connected a fluorescent actin molecule to the gamma subunit, and when they gave it ATP, they could actually see with a video camera that thing rotating. And it doesn't look, looks pretty primitive, but if the video worked, you'd see this whole thing wanging around in a circle. And given that graphic image of the way it works, I think was triggered that Nobel Prize for John Walker, shown here, and Paul Boyer, who worked many years on this. But in 2010, what Walker did was a very simple experiment. He took a picture of the ATPase. Here are the alpha beta subunits where the ATP binds. This is the gamma that connects it to the C subunits that bind those protons. And what did he find? 1, 2, 3, 4, 5, 6, 7, 8 C subunits that therefore bind 8 protons. So when that thing rotates 360 degrees and makes 3 ATPs in its transit around, 8 protons pass through. Now, can we do maths and divide 8 by 3? Does it come out to 3? No. So instead of the old model for ATP synthesis, where you pump a certain number of protons, you need 3 to make the ATP, 1 to transport the ADP and the phosphate, we now have 10 divided by 3.67, because only 8 over 3 is 2.67 instead of 3. Now that might seem strange. When I first approached Leininger, I said, I think the stoichiometry is 3, not 4 for cytochrome oxidase. His first comment to me was, Randy, 3 is an odd number. And I thought, well, the ATPase pumps 3 protons. Sodium pumps 3 sodiums. If I'd have gone up and said, Dr. Leininger, I think the stoichiometry is not 3 or 4, I think it's 2.67, he probably thought I was crazy. But that changes everything, because if it's 10 and 6, and this is now 3.67 instead of 4, and succinate divided by the same thing gives you 2.725. And what did I want the stoichiometry for an NADH to be? 2.75. So this explained all my PO measurements and my resistance in accepting the stoichiometry of 2, or the lower PO ratio. And so what it turned out, everybody was basically wrong. Everybody was arguing and measuring things over and over again and forgot the one factor which could have explained it. The other question, I put this in here just because we do have these, what I call stupid high school textbooks, which tell us we ought to memorize how many ATPs you get from glucose. So being obsessive compulsive in some ways, I figured, well, I got to calculate what it is, because I ought to know by this stage. So I listed all the protons that get pumped when you oxidize NADH, the ATPs you make with thiokinase in the TCA cycle, succinate, got all the protons. Now we have the 2.67, and we got a couple of ATPs made chemically. What does it add up to? It adds up to 29.45 ATPs per glucose plus the 4 that you make chemically, or 33.45, not 38. Now, I don't think they're going to tell high school students, you've got to memorize 33.45 ATPs per glucose, because who really cares? We're going to spend a whole life trying to figure it out. But the other thing people never consider is the fact that if you don't transport the ATP, you don't need these protons to enter. And the PO ratio inside the mitochondria is not the same. And I've never seen any textbook ever mention that. So the number of ATPs is now 41.25. And if you go all the way from glucose, it will be 45. So you could then go on and say, okay, well, maybe half the ATP is used outside the mitochondria. And there's a lot of mitochondria in that cell, so half is used inside. You add those two together, divide by 2, and what do you get? I think it's 39, or it's very close to 38. So maybe 38 is okay. But I don't think it's something people want to spend a lot of time memorizing. Okay, I don't know what the time is here. We're getting short of time. I headed this teaching. As the years went by, nobody was too interested in the inner membrane anion channel, in part, I think, because we weren't able to or did not identify the protein. And if you didn't have a protein to work on, people didn't want to fund you. So as time went by, I went back to what I enjoyed a lot, and that was teaching. I taught in the pharmacology course way back when there was a pharmacology course for medical students. And I don't think maybe it was Dr. Scary said, well, Andy, you worked on factor 13, didn't you? You can do the anticoagulants lecture. But I thought, I don't know anything about coagulation. We were using that for enzyme kinetic studies as a tool. But anyway, that was the first lecture I ever gave. It wasn't quite as traumatic. I mean, it was more traumatic than this one. I think I was up till 5 o'clock in the morning preparing the slides. I didn't realize how long it took and felt like a zombie as I delivered it. But the next time it was a little better. So I listed here, Brad explained all the different teaching I've done. I really enjoy teaching. You get a lot of feedback. I don't want to spend 50 years trying to prove 3 protons versus 2 protons or whatever, okay? And so rather than talk any details, I just put in a few pictures here, taken over the last number of years since I had a digital camera. This one, I noticed the PAs sent a message, so some of them are listening. And this, of course, is a picture of the current class. It seems like an eternity ago. This was back in February, before the onset of the COVID restrictions and teaching from home and learning from home. And here, of course, is Terry Hines teaching that class. So I snapped a few images of him. The main reason I show this picture is when you look at all the smiling faces there, how can you not enjoy going in and talking to them and telling them stories and stuff? So it's very rewarding, more rewarding than publishing a paper that no one ever reads, okay? We also, in our department, which was a pharmacology department, before we merged into physiology pharmacology. So historically, we have what we call the annual pharmacology colloquium. This is a meeting of graduate students from UT or MCO or MUO as it was, the pharmacology students of the University of Michigan, Wayne State University, and Michigan State. 4 students from all 4 schools get together at rotating sites every June, except this last one. This one, 2019, was when we organized it here at UT. And you can see there's a lot of very close people in close proximity here and no masks, pre-COVID times. It seems like an eternity ago, but it's only a little over a year. And here we were on a beautiful sunny day eating all together out in the patio. And maybe we recognize a few faces around here. And I always enjoy the enthusiasm of the students in their research and presenting their materials. And when I go to these colloquia, in addition to, of course, listening to the talks and looking at the posters, I like to record their interactions and their presentations. I think this is Tanoia Harris on the left here, and Jean-Yves Tano on the right. And one year, 2013, Gaurav Mehta, one of our students, actually won, it says first place platform presentation here, but to be honest, I can't remember whether he really got that, because when I zoomed in yesterday, I saw a different name on the certificate. But anyway, things get distributed incorrectly. He won a prize. That's Nick Davis on the left from Wayne State University, and Benedict Lucchese from University of Michigan. He's an older gentleman, I think, passed away in recent years. He began these colloquia with the fall schools way back in 1973, and he was very fond of them too. We got Darren Gordon and others at posters. We have Research Forum here, there's Mark Witten and Dr. Park and Bob Trombley and a couple of Gene Shea's students on the right here. And we got Thea Zwicky, everybody knows, John Turner, Dr. Takashima, and of course, everybody knows Carlos and Sadiq Kuda. Even faculty have poster presentations and forums sometimes. And there's Nikolai. These are all the important people, I guess. Maybe I stuck them all together. We got Dr. Abraham, who was the chair for a few years, up there on the left. Bina Joe, of course, the current chair, along with our dean, Dr. Cooper. And of course, very important people down here. Fareed Murad got a Nobel Prize for his work with nitric oxide. And of course, our ex-president, Dr. Jacobs, and these other important people at the back here. And this one, of course, is Dr. Rosenberg, who was very helpful to me over the years. Gave me a lot of advice on teaching, and was a very fair chairman of the department. Okay, a couple of last pictures here. This is Dr. Joe and our department organized this pre-med summer camp educational experience for high school students last year, June 2019. Again, this kind of event had to be canceled again this year. One reason I put it in here, not just because it's a teaching activity, but that character on the right there, Mark Miller, I'm guessing many of you know him. As you can see, he's doing his job there. He comes in and is very helpful with all the hardware, audio-visual equipment, et cetera, and he's been very helpful to me, or has been over many years at UT, at least prior to 2000, or maybe before that. And social activities. Here's Randy Roosh welcoming a new bunch of graduate students. And here is a huge line of students and faculty here. What are they in line for? Oh, free food. And there's Nick Kiaya at the front, who recently retired, and many others. More students, Candace Williams, Kevin Pan, there's Kate Eisenman, Sarah Moore, I think, down there, and of course that's Candace in the bottom, and a bunch more students in intense discussion. It's nice to see such enthusiastic young people getting into research. And then there's a few older ones still around, Dr. Manning and Dr. Diane Rahman there at the bottom. And anybody, some of you may know Justin Creedon. This was when he first joined the MD PhD program. I think that's Sarah Moore. He caught one of the flying vegetables that Candice threw out to all the students. And of course, here's me with Dr. Turner, making me look like an idiot. But anyway, and of course, we can't forget all the staff who support all our activities. Anita, Lisa, and Deb there. Shot taken back in 2011. We also like to take group pictures, but personally I hate group pictures, so this is my favorite group picture with Diane Adams trying to organize all our students to stand in the right place and position themselves properly. Even faculty have the same issues. Here's our pre-med camp helpers in their t-shirts trying to get lined up for a picture. Again, I keep snapping. I throw a few graduation. Most graduations I like to attend. they're not always the most exciting, so I sneak my camera in underneath my academic regalia and whip it out when I'm set down and shoot some pictures. These were a couple of med students from our class. Everybody remembers Dr. Gold. Seen him on TV a few times this summer, along with graduate students in the background there. Everybody knows Dr. Gohara and Carol Bennett Clark and Dr. Ali, Dr. Gohara again, and of course, Mary Smith. Mary Smith still working hard for our college and been very helpful to me over the years as an advisor to review my anticoagulant lectures, which I started off, of course, knowing nothing, but she helped me out to make sure I didn't say anything that was incorrect. And the very last one here is David Kennedy. He looked so happy holding that big mace that I couldn't resist putting that one in. David, of course, is a very successful faculty member, researcher, and of course, did his PhD at the University of Toledo in our program. And so he's been around a long time and has been a very helpful and colleague and a very productive faculty member. So that's the end of my presentation. I don't know if anybody's still there or you all went to bed or went to watch TV or anything. One big advantage of these kind of presentations is that you can actually leave the event without too many people noticing. But if anybody's still there, I don't know if I meant to answer any questions or not. But I have one postscript here, if you like. Here's James Molnar. I think he was here tonight, making sure all the technical aspects were functioning properly, along with Dan Savick, head of the Alumni Association, who I've also had a lot of dealings with over the years. Okay, so I'm going to escape from here, I think. And
yes, thank you, Dr. Beavis. I've seen those pictures. Was really nice. It's funny to see some of the professors that we have and some of the older pictures and the way that people have changed over the years.
Yes, let's see. Did I stop sharing my screen or did I mess up?
It is.
Stop.
I think you have your whole screen shared still.
There you go. I stopped sharing. Okay. New technology.
We appreciate you coming on and taking the time out of your day the past few weeks. When I've been talking to you and emailing you, it sounds like you've been pretty busy during your retirement. So we appreciate you taking the time to put that presentation together. And yeah, if anyone has any questions, you can put them in the chat or.
Can you see the chat, Dr. Beavis?
Yeah, that I see. I've got my attendee list open and chat down. Oops, I think I just closed it. Chat. I'm a Zoom person now. I'm retired. They cut off my access to WebEx. I see lots of comments here. Can I see these later when everybody's done? Or is there something I don't see any specific questions.
I can certainly save these for you, Dr. Beavis, and send them to you.
Okay, that'd be nice. It's
But yeah, so we do have a small token of appreciation that I'll kind of reach out to you and we'll figure out a way to get that to you with COVID going on to thank you for putting this speech together.
Okay.
Yeah, I'll reach out to you afterwards for that.
Well, you're welcome. There was it took a long time, especially reviving memories. You get to a certain age, you think, can I even remember what happened 40 years ago. And the more you think about it, you come to relive some of those things. It was a kind of interesting experience. And I thank you again for inviting me to present. I'm sorry I didn't put on a jacket and tie, but all the students know I always wear a sweater. I almost dug out my special cardigan I used to wear when it got cold over there. But
It looks like
Looks
we
like
do
we
have a
do have-
question. Rebecca wonders, what helped you to keep going when you face difficulties and failures?
well, yeah, I don't know. You got to keep going. I mean, I put a couple of notes down here which I didn't actually address. You could say, I mean, you probably can answer them yourselves. Did I plan what I wanted to do? I often tell people my plan was to avoid having to go out and get a job, right? Do anything but. And it was somewhat of a surprise to me when I got to the age of 67 and realized it's retirement age and I didn't even get a job yet, because all the things I've done because that's what I wanted to do. And even though you could say, well, research-wise, I didn't get any Nobel Prize. No one accepted my stoichiometry. No one takes any notice of the intermembrane anion channel. And but does that? Well, of course, it matters to some extent, but I did not do it because I was doing it for someone else. I was doing it for very selfish reasons. That's what I enjoyed doing. Like I say, I worked for Hopkins for 2 months without getting paid anything, just to try to get the material written up and published. So in that respect, I wouldn't change anything. I think the reason I put in those pictures of all those different people and mentioned all those different people was that I think as far as my life and maybe many people's lives, what counts more is not their monetary gains or prestige necessarily. What makes you happy is whether you enjoy the work you're doing and you enjoy the people that you interact with. When I think back about my life, I don't think too much. I had to concentrate to think back of all that stoichiometry stuff, and you probably wish I hadn't done that. But the main things that stay with me are the people I've known, interacted with, and they have what makes life worth living, I think. I tell people it doesn't matter whether you're in Toledo or any other place, it's the people that you work with most important. And I've been very fortunate in Toledo and Baltimore and elsewhere that almost everyone I work with has been very nice person and very easy to work with. And it's been a wonderful life, and I don't regret not publishing 500 papers or whatever. And I really enjoyed the teaching. If I hadn't failed at the other things, maybe I wouldn't have had the opportunity to teach. You travel through life and you reach a junction or a fork in the road, as I sometimes people talk about, and you got to decide which way you're going to go. And that's really all I've done. You get to a fork, you reach, and you don't know. I didn't know I was going to bump into Dr. Ghali, for example. If I hadn't, I'd never come to Toledo at all. You sometimes think, well, what if I'd taken a different branch, a different decision at this point in my life? What would I be doing? Well, I can do that on a card game on my tablet because you can back up all your moves to try it a different way. But you can't do that in life, unfortunately, to see what would happen. But I have no regrets about the paths I've taken. And all the people I've known along the way have just made life more enjoyable.
We have quite a few.
Is what do you plan to do in retirement?
I don't know. I haven't had time to think about it yet. My wife, you know, I hope she's not listening, I don't think, but yeah, when I was working, one thing is that for the most part, I was my own boss. I could decide what to do whenever I wanted to do it, as long as I got done what needed to get done. You know, when you're at home and there's the two of you there, then someone else can decide what ought to be done. So, it's different. I would have liked to take pictures. I obviously I take pictures. I take a lot of photographs. I like abstract kind of work, and I bought myself a new camera on retirement to do that. Of course, I had to wait 2 months for it because they told me the Nikon factories were closed because of the COVID and all things like this. And I thought, well, now I can't travel. What am I going to take pictures of? Well, I took my car into the Toyota dealership to get the oil changed. And what did I find? I found a dumpster out back with all this very interesting rust on them. And some of the images I got in there, I think I would like better than I would if I'd traveled all the way to the Grand Canyon or something. And then my wife had cataract surgery at the Toledo clinic. In the parking lot, I found another dumpster, and it had some very interesting rust patterns on there. So I shot pictures of those. So it's one of those things. If I'd have traveled 500 miles, maybe I would have seen nothing that I could take a picture of that was worthwhile or I liked. Whereas just those accidental findings, I just happened to be in that location. You come across these things, and probably it's not the smartest thing to do, but that's the way kind of life has been for me. I kind of point myself in a certain direction and see where it goes, and deal with things as they come along. I always tell students that you need to be aware of these opportunities that arise. Sometimes if you get too fixated on a given goal and you never get there, you might be miserable and you might have missed opportunities on the way that you'll see. And I've done that by either defect of my brain or luck anyway. So I don't know if that answers the questions or just raises more.
So there's one from Lauren Rammel. She said, "Do you still look at all the labels of the over-the-counter drugs at the supermarkets intensely?"
If there's something there I need to know. Yeah, I still have my email. I still get lots of emails on drug updates. So I don't know if those PA students are meant to keep up drug update folders, but since I wasn't there in the fall, I got no idea what they're doing anymore. But I hope they're having a great experience, and I miss interacting with them. And Dr. Andrew Overholzer still does the drug update folder. Well, it's because he was a student in the class, and I brainwashed him into doing it. We got a lot of vaccines to keep up to date with now. Any other questions?
If there's no more questions, I want to thank you again, Dr. Beavis, for taking your time to do this. And
if anybody has any questions, I still have my UT email. They can send me emails. Like I say, whether I was working or not, I just do things that interest me. And if someone asks me a good question, I will answer them.
Oh, I see. One more question that came in. When you reflect on where you see medicine going from here, what are you most excited about?
Well, that's tricky. Well, it's not tricky if I say I'm not excited. I don't know. I don't have an answer to that question. Right now, of course, the big focus is on getting treatments for these viral diseases. Maybe I should have learned more about viruses when I was, you can't study everything though. But yeah, it's you guys, the medical students, PA students, you are the ones who will determine how things develop and what direction they go in. Being an old person and whose health only can decline, I'm guessing, we are always concerned about what's going to happen in the next 10 years. Okay.
I'm not seeing any more questions. I don't know if
Okay. Hope everybody.
Thanks again,
Okay.
Dr. Beavis. I want to thank everyone else for coming out and listening and being here. And
I hope I didn't bore everybody.
oh, wait, Aaron, I didn't see your question. I now see your chat, but I don't see your other question. I don't see your question showing up.
Okay. Well, I just hope everybody keeps safe and keeps well in these crazy times.
And we had one last question, sorry, from Aaron. She asked, who in his life had the greatest impact on your career, and if he plans to publish a photography blog?
A photography blog? Well, I would like to publish things. I mean, you probably don't believe me, but it seems like since I retired, I don't have any more free time than when I was working. I have these ideas in my head. Of course, this it took me a while to put. You may not think it, but it took me quite a while just to put together all this presentation. Mostly just thinking about it. I would wake up at night and thinking back to what was I doing in 1969 or something. It took a fair amount of mental time. But it was I enjoyed doing it. I hope people at least tolerated and always learn something from someone else's story and experiences.
Another question we have, what are the major changes in the PhD journey that you have noticed when comparing your personal journey and the journey of your students?
Well, I did a PhD in England, and because we have everybody gets into a PhD program with a certain grade gets a stipend, which was very nice, but it only lasts for 3 years. So we have to do everything in 3 years. So here, students take longer time, and maybe in part because they are funded by their major advisor, they spend longer on their PhD and required to publish more than when I was doing mine. But that's just different. I wish my advisor casually mentioned to me several times, nowadays, I mean, this was back in 1974, nowadays you need to get publications to stay active. And because of the circumstances and the lack, I would say lack of pressure, and maybe I didn't do those things. The only things I regret in my life are the things I didn't do. And again, sometimes I wake up at night and I remember experiments which were very interesting that I'd done that I never followed up on or never wrote up. And those things I didn't do are really what worry me more, if you like, than anything else that I did do. It's things you didn't complete. There must be some kind of mental condition where you feel pressure to complete things, even when it's not necessary. It's, maybe I should see a psychiatrist. But it's helpful because my wife is the complete opposite. She feels an obligation to start things and no obligation to finish things. So if she wants me to get me to do something, she just starts it, makes a big mess, and then I feel compelled to finish the job. So I guess in that way we work well as a team. Any other questions?
We got two more. One from Dr. Worth. He said, the
Dr.
common
Worth.
theme I got from your excellent presentation is that of perseverance and the fact that you've retired too young. When can we get you back?
Yeah, well, people always say that. Who knows? I've one thing that has occurred to me really over the years, the way you make these decisions at different steps. People always say, "Well, you're going back to England or something." I don't see things never go back. You can't go back. There's no undo. Let's go back to here. You always got to move on and look for new things, and just keep your eyes open. Like I say, this past year, of course, was something that none of us expected. I never expected I'd have to learn how to use WebEx and Zoom and record lectures. I thought it was impossible. I can't record lectures. I can't sit in front of a microphone and talk to myself. When I was 12 years old, there was no way I would have ever got up in front of a classroom or a school full of kids and been able to utter a word. I would never be able to teach a class, but you do it and then realize, well, I didn't die, so maybe I can do that. So it's life kind of goes on. It's hard to go back. Looking for new things. I think as a scientist, we're just kind of like explorers. I do that in my photography. I like to explore. I like to move around and look for things, find things. And in the same way, I approach research. I explore an area, an ion channel, its properties and what it does, and that's what I like to do. Once I understand something perfectly well, I kind of lose interest in it. It's I always tell students, I said, this lecture is just a rehearsal for the next time. I tell the PA students, oh, I'm just rehearsing for the lecture to the medical students, or when I'm giving a medical student lecture, I'm just rehearsing for the next time I give this lecture. It's once I have it perfect, maybe I would lose interest in it. I think one thing about teaching is I always enjoy it when I teach something, and each time I give it, I learn something new that I didn't know, or I see something from a new perspective, or see it from a different angle, different point of view, different significance. And that's what kind of drives me, I think, or drove me to work on those lectures and give them so many times. It's each time was slightly different. So I never rehearsed any presentation ever, even a 10-minute talk on a paper. I just watch the clock and try to keep the speed that'll get me to the end before the time runs out. Have I avoided all the questions so far?
So we got one from Kada. She said, "What should the next generation of medical professionals be careful of?" And then, where could you see future scientists falling short?
Falling. These are way too difficult questions. That's. I'm a detail person. That's a big picture. That would something that keep me awake all night just trying to figure out an answer. I usually tell students, send me an email and I'll think about it and let you know. Maybe Brad, you want to answer that one.
Yeah, I'll leave that to you. They can send you the email. Brandon Sharkey said, "Can you mention glaucoma just one more time for old time's sake?"
Glaucoma. Okay, all those drugs. Can you make a list of them all? Where they work, what they do? Do they speed up drainage or inhibit secretion? And don't get all the M2 inhibitors mixed up. Yeah, it's a fun disease. Nice and small, you see, very focused.
Another question is your favorite lecture to give the leaky bucket?
Is it? Well, you might think so. A lot of students think I'm a bit nutty about leaky buckets, but I think it comes from a background in enzyme kinetics, where we talk about steady states, and my obsession with thinking of analogies. And to be honest, if you lump that together with all the basic principles, in some ways, I always, as a scientist, I like the basic principles more than the individual areas, topics, because principles are always there, always useful, and can be applied to every drug, if you like, or any situation. And therefore, to me, that's something very valuable to know. Knowing one individual drug is obviously important if you're interested in a specific disease, but my brain is not big enough to remember details about individual drugs, really. And so I really like the principles. It's the basic science is what we're looking at all the time, is principles. We study new pathways, new processes, new things, and really, or at least I do, what I'm looking for is to try to extract out of that some principle of how things work. You look at 10 different processes doing similar things, and you see how they're similar, and you determine what the principles are. So principles, I think, is always it has always been of interest. I was quite happy when Dr. Wilkerson left, and I took over his lectures on the principles. Everything else is a bit, uncertain. And requires too much memorization. I don't like to memorize things. I like pictures. I see a picture. I have to be able to see it. See it, smell it, walk around it, and identify it, recognize it from any direction and angle. And then you understand it, not a simple memorization. Some things you have to memorize, but I'm not very good at that.
Yeah, Sarah from the chat said Bimatoprost with the elephant's long eyelashes photo. So it seems like your photos are helping people remember things.
Oh, well, maybe. Yeah. I just, it's when I see those things that helps me remember too. You know, it kind of amuses me to, and I try to relate the basic principles of pharmacology like with everyday things. Mention commercials on TV. They still they can list all the side effects of a drug in like 15 seconds or less. And I think, well, do I understand each one of those? Can I even think that fast? Um, it's it's uh, it's good to relate what we need to know to everyday experiences. Helps us understand them and see the relevance.
Then Anita Easterly said, Dr. Beavis, I need your handouts and exam questions by Monday for old time's sake.
Okay, Anita. I'll get working on them. Is it weekend yet? Thank you, Anita. Anita was very helpful to me over the last few years, quite a few years, and always good to work with.
But that's all I see in the chat, so I don't see any more questions coming in.
Okay. If I click this red X, I'm out of here, am I? My wife will be telling me I've been boring you all too long.
Oh, not at all. Yeah, but like we really appreciate you coming on again. I can't thank you enough for, taking the time out of your retirement to put this together. And
You're welcome. Keeps me busy. Keeps me having to go out and shoot pictures. Well, I told those PA students I give a lecture on on bone drugs, osteoporosis, and osteoblasts and osteoclasts. And I always think about the road repairs, pulling up the road and relaying the tarmac. And this year, when I had to make them at home, that very minute I was working on that lecture, these guys came to scoop up the road right outside my house. So I couldn't stop. I had to stop working on the lecture, run out to my front porch, take a picture of it, and put it in the lecture as a example of an osteoclast taking out the road surface. And then 2 days later, I came to lay the top down. I said, hey, we need teamwork here. It's a model. But anyway, just an excuse to run and take a picture.
But yeah, so I think that's it, and thank you everyone else for coming. And
well, thanks again, Brad, for inviting me. I was excited that you would even think about it. It never crossed my mind, but I appreciate it.
Absolutely. And I'll be reaching out to you about how we'll get you your gift too afterwards.
Okay, very good. Thank you.
All right. Yeah. Thanks everybody.